Okay, so again, apologies from Ben. This is really not professional for all of us here, but it just happened. It's just one of those things. And if these aren't weird enough times to, in fact, figure out that other weird things are going to happen. So Ben enrolled in the Planetary Science Summer School run by JPL, which is a great experience, by the way, for people if they haven't done it before, for students and postdocs. And of course, they have right now, their big presentation to pitch their mission, and he is a major participant in that. So he sends his regrets. He made the right decision there. He has I hope, able assistant to present his work here. So this represents information that is related to some new discoveries that we've made that are related to the big question of what is the climate on Mars and at the Noachian, and what is the evidence for the geological activity that all of us agree has significant support for running water, for collection of running water into lakes, and possibly even draining into oceans in the northern lowlands. So the bottom line here is that if you remember our earlier discussions here a little bit, basically Noachian-aged craters on Mars differ significantly from later ones, and I'll talk about this more in a couple of talks, or is it going to be, I guess it's the one after the break. Based on the left here, we can see evidence for classic Noachian craters. Craddock and Howard and their colleagues, Ross Irwin, Matsubara, and others have really done a great job in documenting and characterizing these things. And what they find is that these Noachian craters are flat infill floors and lowered, actually missing rims. The rim is actually there, but the rim crest is degraded, and the ejecta deposits are pretty much gone. And they're often modified by fluvial erosion. You can see evidence for a fluvial channel here. And this led them to hypothesize that Noachian Mars was warm and wet, maybe warm and arid, but that the mean annual temperature was above 273 K, and rainfall precipitation was really the dominant thing, with rain splash being the diffusive degradational process responsible for these craters. And again, a terminal phase of late Noachian climate optimum that caused the rainfall rate to exceed the influx, the essentially infiltration rate, and cause runoff as we see here. So this is basically the Craddock and Howard model. And this is supported by a lot of data, okay? And in addition to that, we have two other kinds of features related to craters, and that is lakes, craters which have lakes in them. These are divided over the years into two different types. These are open basin lakes and closed basin lakes. In closed basin lakes, you have essentially a channel coming in, such you can see here. This is Gale crater, for example. And the channel enters, there's a delta here, actually, a fan, and then essentially fills a portion of the crater up. But we don't know with these whether it filled it up completely. It didn't completely fill it up to overflowing because there's no exit channel, okay? So open basin lakes, on the other hand, such as Jezero, where Perseverance is scheduled to land right about here, is in fact one in which we have valley networks entering, and these are channels, fluvial channels entering, and then filling the lake up, and we know it's filled because it exits out the other side. So these are the two kinds of lakes, an open basin lake and a closed basin lake. In our work here, following up on work from Ross Irwin and studies, we've been able to find some other types of lakes. There's actually work by Solis et al. That shows that there's some groundwater-fed craters as well. They interpret a series of craters that occurs at lower latitudes. This is way below the area we've been paying attention to in the upper Highlands. But in the Hesperian, from about 3.5 to 3.7, they documented what looked like essentially sapping valleys that in part have fed delta-like structures here. And this is a diagram of essentially the kind of thing you can see there. So what we found here, following up again on work by Ross Irwin, who did a kind of a classic study in here about the characteristics of these craters, more on a general scale, not so much the details of each crater. We found crater B, which is named by Ross. It's a 54-kilometer diameter crater. You can see it here in this CTX image. And here it is superposed on the topographic map. This is the Hellas Basin. It's northwest of Hellas. It's one of these craters in this area here. And you can see there are a lot of open basin lakes and closed basin lakes indicated by the red and green. and also valley networks shown in the blue here. So this is an area of definite water runoff and water collection. But the distinctive thing about crater B, in addition, is that it is an endorheic lake. It is a closed source endorheic lake. So endorheic lake really means that the water doesn't flow out of the lake. It doesn't mean, endorheic lake, one type of endorheic lake can have an influx channel, that's an open basin lake, but it doesn't have an exit channel, so it's an endorheic lake. This one is quite different in that we don't see any input channels into this lake here at all, okay? So we interpret these features to be the site, facies associated with the lake, and you can see here a little bit of interpretation of what we're looking at here, okay? So this is 54 kilometers in diameter, and it has a whole series of facies in here, okay? It's a closed source drainage basin that has no external drainage into or out of the lake. And so that's why we call it a closed source drainage basin. So where did the water come from? That's the big question. So we see a variety of facies here. We see a debris apron around the base. This doesn't appear to be a fan from debris shed from the rim per se. We see a very distinctive scalloped rim around the edge, and I'll come back to that in more detail. A debris apron, and then emerging from underneath this debris apron are a series of, shown in blue here, are a series of ridges, and I'll show these in more detail. These are inverted fluvial channels that originate from basically what looks like local drainage at the base of the crater wall. Then in the middle here, we have essentially two basins, one circular one here, and one more irregular one. This appears to be superposed onto this one. And these look like deflated sedimentary rocks from fluvial channels that flow into and drain into the lowest parts of the lake here. So the inverted fluvial channels on Mars that have been mapped elsewhere by a number of workers typically date from the late Noachian to the early Hesperian. And this is consistent with the resurfacing age that we get from crater counting on the floor of crater B. So these things could be late Noachian, early Hesperian, another type of lake, a closed source and drainage basin. And if we take a look in detail at the characteristics of these kinds of deposits, here's a view of the same map just blown up. One of the things that was not quite clear in there are these upslope facing scarps that we see, and we'll come back to those as well. So the scarp is facing upward, but it's cuspate also all the way around, and it is very closely, these are very closely correlated with essentially alcoves in the wall, but they're not kind of classic sapping alcoves or alcoves associated with crater erosion typically. On the right, you can see a perspective view. This is if you were hovering over the middle of the basin and looking about towards the edge of the basin, about 20 kilometers, okay, in this direction. You can see here these inverted channels. We interpret them to be fluvial ridges, and I'll provide evidence for that momentarily. And from this topographic map, this is a high-rise topo DEM, you can see that the pink is high and the purple is low. You can see evidence here for, in fact, these low bait features are here, and then this sediment layer, essentially debris apron, and then from underneath this debris apron is coming these inverted fluvial channels. So if we take a look at these in more detail, these are really amazing. I mean, these are absolutely incredible. We see basically proximal ridges. These things come full bore out from underneath this sediment right at the base, a little bit higher than the base of the crater wall. And they converge here. You can see them joining and forming larger channels, which form ever larger channels by joining here. And they flow into the low area, into one of these trunk ridges sometimes, and then, of course, into the lowest part of the lake region. Now, if we take a look at the southern part, that was in the eastern part, the one you looked at in a perspective view, we also see the same type of feature. Here is this lake deposit that we see here. And we see a number of channels, in particular some which have antibranching ridges that emerge and then extend down and essentially empty into this lake deposit. This lake deposit, in fact, has been highly modified by aeolian activity. You can see all these parallel dunes here in the higher albedo region. So how does a closed source drainage basin form? Well, clearly there are no external drainage paths. So fluvial dissection from regional catchments, as we see in Jezero and Gale potentially, are not an option here. We just don't see them. Okay, we do see valley networks in these regions further away, but they don't drain into this crater B itself. The other possibility is groundwater sapping. And again, we see no evidence for the kinds of features that Solis et al. Saw at much lower elevations later on in the Hesperian. So what's the deal here? So one of the things that we've been looking at on Mars over the course of the last few years is coal-based glaciation on Mars. And so if we take a look, we're gonna flip to the Amazonian now, and we know that, of course, with the lower atmospheric pressure, the current temperature at Mars is about 214, 217 K. It's really cold, okay? And so we're not talking about wet-based glaciation, we're talking about cold-based glaciation. And the difference is that wet-based glaciation, the pressure melting point of the ice and the water is at the base of the glacier, so it creates all sorts of scouring and drumlins and eskers and all sorts of features associated with wet-based glaciation. 5 field seasons in Antarctica have enabled me to look at a lot of these coal-based glaciers, and there, essentially, the glacier is frozen to the bed, and because it's permafrost, and deformation takes place within the ice, and so these glaciers can flow out onto terrain and then ablate back, and you see no evidence because they don't interact with the underlying. All the deformation, virtually all of it takes place within the ice itself. So we've been able to document examples of these things, and we find, in fact, what we do see is cuspate features here, which are the lobes associated with the terminal advance of these individual glacial lobes. And we see evidence for scarps and features associated with these things as mapped out. This is this, but just shows you, illustrates the features here, these upward-facing scarps, etc., as the ice is ablated away. And indeed, we see essentially top-down melting from some of these features as well, where there's evidence for heating and melting of the glacial ice and runoff with inverted channels. So these things are occurring when the obliquity changes on Mars, and we end up with, in fact, snow and ice being deposited at mid-latitudes and even tropical mountain glaciers. And so as the climate changes, these things form and evolve, and then they ablate away when the climate changes back to essentially a lower obliquity and more polar deposition takes place. So what about coal-based glaciation in the late Noachian? Well, work by Wordsworth et al., which I'll talk about in much more detail in the next talk, shows, in fact, that if you have an atmosphere that is more than a few tens of millibars in atmospheric pressure, like 100 or 300 millibars, the atmosphere becomes dense enough that an adiabatic cooling effect kicks in. And essentially, even though the mean annual temperature is well below freezing, way below freezing, as a matter of fact, you in fact get snowing out of the water from the atmosphere onto the much colder surface caused by the adiabatic cooling effect. So water migrates here, and what you produce is a deposit of ice and snow in these areas here. So the question is, could these types of deposits be related to the kind of features we see? Could this closed basin, Endorheic, closed source lake, be related to top-down melting of glacial ice? So if we take a look at the features in this, in fact, this is you can see the channels here, you can see the sediment layer, and you see these lobate features here and these upward-facing scarps. These are very reminiscent, although more degraded, of, in fact, the types of features we see in Amazonian craters that have undergone clear evidence of coal-based glaciation. So the question is, could we have had in the Noachian and crater B, a 54-kilometer crater diameter crater, could we have had glacial snow and ice around the margins of the crater flowing down into the crater, but a temporary or short-term heating event that caused top-down melting and drainage of this into this Endorheic lake? This would be the sediment that is in the proglacial sediment. We see dozens of examples like this at coal-based glaciers in Antarctica, where seasonal melting produces top-down melting and drainage to create the kinds of lakes that you're all familiar with that occur in the Antarctic dry valleys. So in conclusion, this closed source drainage basin in crater B really represents a localized Noachian crater degradation that is distinct from fluvial to dissected and groundwater-fed crater lakes on Mars. It's kind of unique in this way, and we interpret one possibility for the origin of this is that essentially melting of glacial ice on the walls of these craters, like we see in dozens and dozens of craters in the Amazonia. Top-down melting of that by a essentially phase of heating, a temporary phase of heating, could have in fact caused meltwater to flow down and into the basin, and then essentially ablate and leave the sediments and the inverted fluvial channels we see. So this is the area here. This is a map of the equilibrium line altitude of +1 kilometer predicted by the climate models. And you can see that this our crater should be in the area here of extensive snow and ice. And so indeed, we think this might be consistent as an origin. So we're looking further into an origin of this crater. And we're also looking, of course, in the next steps for regional characterization here. Here's Endorheic crater B. There are dozens of other craters around here. Many of them have these same characteristics. So we're now in a search for the characteristics of the rest of these craters to see if they either support or refute essentially a glacial melting hypothesis for this interesting Endorheic closed basin lake. Thank you very much.
Thank you, Jim. Much appreciated. Are there any questions?
There are none currently in the chat. I spoke too soon. Again, apologies for pronunciation. Denise writes, craters or valleys are forming Noachian-aged, and some landslides observed in this area can be determined by Amazonian-aged, or are Amazonian-aged. Can we say here that the ice is underground and surface shapes are formed after a catastrophic event?
Well, certainly ice is underground. And I'll talk about this a little bit in the next talk after the break. Essentially, if early Mars is cold and icy, okay, not warm and wet, then there is a global cryosphere. So and it's very likely to be ice submitted based on the water budget for Mars. So in that case, you definitely had kilometers thick cryosphere of solid ice. It would mean that, and we'll talk about this a little bit in a few minutes, it would mean that the hydrological system was horizontally stratified and groundwater was not related to what's going on the surface, much as it is in the Amazonia today. So I think there would not be a robust circulation in the subsurface that would be in contact with the surface. There would be a lot of activity related to hydrothermal activity in the subsurface, and that could be also another candidate for the formation of alteration products such as clays. But I don't know of. Let's see. You're asking about a catastrophic event, Denise?
Sorry, switching applications. I don't see the word catastrophic. Oh, wait, yes. Can we say here that the ice is underground and surface shapes are formed after a catastrophic event? So it takes a catastrophic event to, I guess, bring that ice up and create the features that you see.
If you're talking about Crater B in particular, I don't think that, so Gale Crater, for example, is a early Hesperian impact crater. And one option for some of the features that we see there in terms of the aqueous properties is that it is groundwater fed, okay? That it is indeed, that the impact event itself from work of Osensky and Grieve and many, many other colleagues in Canada, they have obviously shown that the characteristics that in fact, the impact event itself, the energy partitioning associated with it, can impart heating to the substrate, which will in fact breach the cryosphere potentially, and then allow groundwater to flow out, okay? And that could be what's going on as a source for the water in Gale Crater itself. But over the course of tens of thousands of years, of course, it will respond to the ambient atmosphere, and that will be sealed up. Exactly how long that lasts and how that process works, it's hard to map. It's hard to essentially model 50-kilometer diameter craters in a test tube, which is unfortunate, but it's a fact. So we don't know exactly how long that would last, but it is a candidate process. That is groundwater release by an impact or ground ice melting by impact. What argues against that is that these things seem very closely related to this sediment band, which is in fact slightly up the ridge here, and they all seem to form at the base of these lobes and in relation to this upward facing scarp, which is very typical of where the ice stops in the Amazonian craters. So I think it would be rather hard for all of these things to be coming out as groundwater events. And in particular, this crater is pretty degraded, okay? So you would need to have an impact, you would need to have enough period of time to degrade it, then you would need to have all the water come out right along these little margins here and flow down in, and you would need to have only enough water so that it didn't fill it up. To me, based on our based on our water budget calculations, a much more likely scenario is that top-down melting of wall glaciers, such as we see in the Amazonian, is more of a candidate. But it's an interesting hypothesis to keep in mind.